Lesson 5, Units and Measurement. In this lesson, we're going to be taking a look at another fundamental quantity, mass, as well as another quantity which is not fundamental, weight. Our objectives are first to be able to define both of these quantities. Next, you'll want to also be able to tell the difference between the two. You'll want to be able to measure the mass of an object using a triple beam balance. You'll also want to be able to mathematically determine the weight of an object if you know its mass, as well as the opposite, to determine the mass if you know the weight. So we start by taking a look at a contrast between mass and weight. The problem is that in the United States, we have a tendency to equate mass and weight. But the problem is, they're not the same thing. Let's see why. We'll start by taking a look at mass and defining it. Mass tells us how much matter makes up an object. In other words, this is how many molecules or atoms are inside an object. The mass of an object doesn't change regardless of where it is located. It is always going to be the same amount of matter in the object. The MKS unit for mass is the kilogram. If you remember when you were watching Bill Nye, a kilogram was defined as the mass of 1 liter of water. The British system also has a unit of mass. It's called a slug. It's hardly ever used, but it does exist. The way mass is generally measured is by using a balance. So if you've ever seen a scale, you usually see that it has two sides. You put your object on one side and an equivalent mass on the other side until it balances. Now let's take a look at weight. Weight is a planet's gravitational attraction on an object. Gravitational attraction is a force. An object's weight can actually change based upon where it's located, because gravity can change based upon where two objects are. We'll see this in a little bit more detail when we get to lesson 14. But this is why weight is not a fundamental quantity, because weight can change. Mass cannot. When we take a look at the unit for weight, you'll notice that it's named after a scientist. After we get past our fundamental units of the meter, the kilogram, and the second, you'll notice that the units are going to be named after scientists, the ones who studied them. In this case, for the MKS unit, gravity was studied by Isaac Newton. So Newton is the unit for weight. Newton is going to be abbreviated as a capital letter N. The British unit for weight is the pound. It's abbreviated as LB. Now that may seem a little odd, but that actually comes from the Latin. Libre means weight or scale. So LB, Libre. We measure weight by using forces, since weight itself is a force, usually by stretching or compressing springs. An example of this is if you were to go to a grocery store and you go to the produce aisle. You usually see a scale hanging there. You put your fruits or vegetables in the scale, gravity pulls down on the scale and makes a dial turn. Inside the scale is a spring. The spring is what's making the dial turn. So by stretching the spring, we can figure out the weight of the object. So we use a force to measure a force. Now let's take a look to see how we measure mass. One way is by using what's called a triple beam balance. Here's two pictures of triple beam balances. It gets its name because it has three beams. One which is measuring the hundredths place, one which is measuring the tenths place, and one which is measuring the ones place. Let's take a look at the first one. When you're taking your reading, you always start with the hundreds. You could see that we're at 500, so we would put down a 5. The next is at 30, so that would give us a 3. And the last one actually not only gives us the ones place, but takes us to the tenths place as well. So if we take a look to see where the arrow is, we could see that it's about 4.2 or 4.3. We'll say 4.2. So our overall answer is 534.2. Triple beam balances are always going to measure in grams. Always remember to put a unit down because it's a measurement. Let's take a look at the second example. Once again, we start with our hundreds place. So we're at 700. We put down a 7. Our tens place is a 0. Our ones place is going to be a 2, and it looks like it might be around 2.6. So we have 702.6 grams. Now let's see how we can determine weight if we know the mass. This is actually going to come about from using a formula. Our formula looks like this. The FW means the weight in newtons. We use an F because weight is a force. We put a little subscripted W after it so that we know that the force that we're talking about is weight. FW is one thing. It is not two different things. It's a symbol with a subscript. M is going to be the mass of the object, and that's always going to be in kilograms. It needs to be in kilograms and not grams for this to work. And that's because of G. G stands for gravity. Gravity for the Earth is 9.8 newtons per kilogram. That means that on average, because gravity really isn't the same everywhere on the Earth, so on average, gravity on the Earth is about 9.8 newtons on every kilogram of mass. That G is going to be a constant. It's going to show up a lot from now until the end of the semester. So it's a number that you're going to need to be familiar with. As a constant, it's not going to change. In much the same way that pi is always 3.14, lowercase g will always be 9.8 newtons per kilogram. Notice that I stressed that it is lowercase g. That's because you're also going to encounter some formulas that have a capital G in them. Capital G stands for something else, so you want to be able to tell the difference between capital and lowercase letters. Now, instead of writing the formula the way that we have here, we could also put it in the form of a triangle. Whenever we have three quantities in an equation, we could do this, and it will actually help us figure out how to solve the problem, especially if you're not too good in algebra. We'll go through how to use the triangle to solve the problem when we do our two examples. You'll now want to put these formulas on your formula card. This is going to be the first formula that goes under basics. You could put down, besides the formula, the value for G, so that you don't need to memorize it, but you will become familiar with it. Notice that by looking at this formula, that there is a relationship between mass and weight, but they're not the same thing. So in the United States, we do say that mass and weight tend to be the same thing. And on the surface of the Earth, there isn't too much of a difference. But the fact is that weight can change, and it's not a fundamental quantity, and it's not mass. Let's try some examples. For the first example, we want to be able to say what is the weight of a 20 kilogram stone. So we identify what we're looking for. What is the weight? And our symbol for weight is FW, and we know that we're going to expect this to come out in newtons. The next thing we want to do is we want to put down our formula. You could either put down the formula in its traditional form, or you could put down the formula in the form of the triangle. In going through the formula, we can now gather information about our question. We see that we need to have a mass. Well, 20 kilograms would be a mass, so that would be M. Next in the formula, we see that we need G. G is not given in the problem, but you're expected to know that G is going to be 9.8 newtons per kilogram. Now we can substitute in our values. In the normal formula, we put the 20 kilograms times the 9.8 newtons per kilogram. In the triangle, we substitute the 20 kilograms for the m and the 9.8 newtons per kilogram for the g. In the case of the triangle, we can see that the 20 and the 9.8 are next to each other. When you have two things that are next to each other, that indicates multiplication. So that's telling us that we need to multiply those two quantities. Notice also that I put the units in. That's because when we multiply, we could see that they would cancel and we would get out units of newtons, which is what we expect. So that when we multiply, we get 196, and our final answer is in newtons. For our second example, we want what is the mass of a 20 kilogram stone. So in this case, we're looking for the mass, which is m, and we expect that to come out in kilograms. But our formula is still going to be the same. If we use the formula in its traditional form, we're going to have to do a little bit more algebra. We see that in order to find the mass, the other two things that we need are the weight, in this case 20 newtons, and gravity, which once again, not given in the problem, but you're expected to know that it's 9.8. We could substitute in our values. In the case of the formula, the 20 goes on the left, the 9.8 in for g on the right. In order to get that m by itself now, we're going to need to divide. If we use the triangle, we could put the 20 in for the Fw on top and the 9.8 for gravity on the lower right. And we could see that the 20 is over top of the 9.8, indicating division. So in this case, we know that we're going to have to divide without having to worry about what we need to do algebraically. The units are in and we can see that newtons are going to cancel. We're going to be left with kilograms. And our mass comes out to be approximately 2 kilograms. It's a little bit over, but we'll round. And that's our final answer.